Hello and welcome to this video on EDEXCEL Chemistry Unit 5 walkthrough video. So this video is looking at obviously the general principles of Chemistry 2, transition metals and organic nitrogen chemistry, including a synoptic assessment as well. So the whole point of these videos is to go through the past paper and to not only just go through the answers, but to help show you methods and explanations as to why it's the answer as well, and little hints and tips as well on the way. It might be quite a good idea to see if you can get a hold of this paper. They are freely available on the Pearson website, as they're now called, or EDEXCEL website, and you can have a go at the questions yourself and then use this video to have a look at the answers. Also on the left hand side, as you can see, there's a little menu on the side, so if you decide you don't want to do the multi-choice questions at the start, you can actually do the questions which are later on in the paper, and you just click to any one of them links and you'll get the answers there. As you can see, this paper is an hour and 40 minutes, that's how long it would take, as you can see on there. So this is the June 14 paper and it's worth 90 marks, so let's make a start. Okay, so always start with these multi-choice questions, and so it says, in which of the following ions does the metal have an oxidation number of +3? So what we have to do is just quickly work out the oxidation numbers of some of these. So you can see here, this one would have an oxidation number of +6, this manganese, because we have 4 lots of -2, which is the oxygen. Overall charge is -2, so that means this is -8, so this manganese must be +6, so that's not the one. Vanadium oxide, again, that's -2, so to give you a 2+ charge overall, vanadium must be +4, which you can see here isn't the case, so that's not what we're looking for there. This one is -4 over here. Cyanide has got a -1 charge anyway, so we've got 6 of these, so that means the ion here must be +2 to make sure the charge is balanced. It's not that one, so it is actually this one here. And if we write our oxidation states, you can see that we have our plus charge here. This Cl is going to be -2 because we've got both of them. We have an overall positive charge on here. Water's a neutral, so therefore our chromium has to be +3. And that's going to give us our overall charge here of plus. So actually the answer is D for this one. So it's just quite a bit of working out. Okay, and the next question says copper metal is oxidized to Cu2+ by nitrate ions, which are reduced to nitrogen monoxide. By considering the changes to the oxidation numbers of copper and nitrogen, it can be deduced that this reaction. So we need to look for 2 of these. Now copper metal has an oxidation state of 0 because it's an element. This is obviously +2. So this has been oxidized by +2, and for this to be oxidized, something has to be reduced by the same, effectively by the same value. The nitrate ions, nitrate, obviously this 5 tells us that it's +5, and they're reduced to NO, which is this one is +2. So effectively what we're looking for is that the copper has been oxidized, but something would have had to have been, for this copper here, would have to reduce the nitrate ions by 3 levels. So what we need is 3 lots of copper to reduce this by 3 levels, and we need 2 moles of nitrate ions, which are these ones here, because that's going to oxidize the copper by 2. So you're just looking for the opposite basically. So the nitrate needs 2 moles and the copper needs 3, so it has to be C for that one there. Okay, right, on to the next part. Okay, so question 3 is shown as a cell. So you can see, so the diagram below shows a cell setup between a copper metal / copper 2 ion electrode and a reference electrode known as a calomel electrode, which is this one here. So you can see we've got the copper metal, the copper sulfate solution, there's a salt bridge voltmeter, and there's our reference electrode. Okay, so it says under standard conditions the EMF of this cell was -0.07 volts. The standard electrode potential of the copper metal or copper 2 ion electrode is plus 0.34 volts. Hence the electrode potential of the calomel electrode is, so this is just a very straightforward calculation, so you just have to try and remember really the E0 of the cell is effectively the E0 of the right hand side minus the E0 of the left. It did say this was standard conditions, so all our numbers should be just standard values. Basically, the E0 of the cell is minus 0.07 because they've told us that. We need to work out the calomel, which is the one on the right hand side, so I'm just going to put X there. And we're going to minus that by 0.34 because that is the voltage of the left hand side, which is this one here. And then if you rearrange that, we just nudge this over here. So that's minus 0.07 plus 0.34. And then obviously we don't really need a calculator for that. So that should give us 0.27. That's positive 0.27. So it's there. Make sure you remember this equation because if you didn't, you might pick up on the wrong answer. Okay, right, so on to the next question. So this is quite a tough one, this. It says for the reaction, and we've got NO2 gas to N2O4 gas. At 450 Kelvin, the total entropy change, delta S total, is negative. Hence, the equilibrium constant Kp for this reaction at 450 K is... Now, we've got a lot of things going on here. So the first thing we need to identify is actually going forward this way. This one is effectively a negative entropy going this way. So I'm going to just write that on there. So we've got a negative delta S going that way because we're going from a more random arrangement to a more ordered arrangement, going from more moles to less moles. So that's not entropically favorable. And effectively, as we... the temperature is 450 Kelvin. That's quite high. That's higher than room temperature. So what we can say is that actually, again, this is something that you'd have to remember because normally this is drawn or this is deduced from a graph. They haven't given us a graph. So as we increase the temperature, then effectively it's less likely that delta G is negative. So we're going to put on there, or we can say that there's more. We'll put delta G is more likely, should we say, to be positive. Okay, so that's important because actually if delta G is positive, that means the reaction is not feasible. It won't actually work. Now, because the reaction is not feasible, what that means is that in terms of our equilibrium here, we're going to have more of this and less of our product. It's going to stay on the left hand side because the delta G is telling us that the reaction is not very likely to occur. So equilibrium is going to shift to the left. Now you might think, well, where does that fit in with Kp? Well, the Kp value here when delta G is positive is less than 1, and so therefore the value has to be positive, but the value is going to be smaller than 1, so therefore it has to be C. Remember, our Kp, which is partial pressure, is the partial pressure of products divided by reactants. So if our number, this number is going to be bigger as a fraction, that's the bottom number for Kp, then that means obviously our value is going to be less than 1. So that's quite a tricky one. But as a general rule, to maybe help you out a little bit, Kp is greater than 1 when delta G is negative, and Kp is normally less than 1 when delta G is positive. So yeah, there's quite a bit to think about that one, but that one's C. Okay, on to the next question. Right, so we've got the standard electrode potential for two half reactions are shown below. And we've got two half equations here. Which of the following processes is thermodynamically favourable? The reaction of, and we're looking for the reaction. Now we can do something called, I quite like the anti-clockwise rule. The idea is that we have two half equations. We put the most negative on the top, in which case this one is already, and we do our anti-clockwise. So we go back that way and back that way. So what that's telling us is effectively the Cl minus will react. See, that's the start of the arrow here. The Cl minus will react with CO3 plus, and that will form half Cl2 plus CO2 plus. So this kind of anti-clockwise rule tells us that these two will react because these are both at the start of their respective arrows. So effectively, the answer to this one would be cobalt 3 plus reacting with Cl minus, and that's going to form your Cl2. So this one is going to be D. There you go. So that's how I work that one out. And then question 6 says a solution of potassium manganate 7 was used to determine the concentration of iron 2 ions in solution by titration in the presence of excess dilute sulfuric acid. With the potassium manganate 7 in the burette, the end point of the reaction is when the solution in the conical flask turns. So this one we are using permanganate, and it's just the one you have to remember. It's this classic pink color that we get at the end point of this reaction. Okay. So the next one says if insufficient acid is added, the titer value is right. So let's just very quickly write out our reaction here. So we have MnO4 minus. This is our manganate, and we're going to form Mn2 plus because that's what it reduces to. Now, if we balance that, we'd need 4 lots of water on this side. We'd need 8 lots of H plus on this side, and we need 5 electrons. Okay, so there's our reaction there. And then if we look, obviously we're reacting it with iron, it said here, so concentration of iron 2. So we're going to write our reaction up. So it's going to be Fe2 plus, and that's going to be oxidized to Fe3 plus. The electron is going to sit on this side. There's the electron there. We balance out these electrons here, so they've got 5 there and a 5 there. Cancel them out, and we're going to rewrite out our equation. So we're going to have effectively MnO4 minus will react with 8H plus Fe2 plus, and that will form Mn2 plus they should be 5s because you multiply the whole equation by 5. So put me 5 there. 5 Fe3 plus 4H2O. So what we're looking for is basically we're looking for the consequence of not having enough acid in there. Now, what the role of the acid is effectively to help reduce your manganate to Mn2 plus. So if we don't have a lot of this, then what we're going to effectively do is this is going to give us what we need to do is we need to add more of this effectively, because not all of it is being reduced. So it would give us the impression that we have a high amount. So it's either one between these two, and effectively what would happen is our manganate would actually produce, the oxygen would be released. Remember that the H plus is there to react with the oxygen to form water. So the H plus wasn't there. The oxygen would actually react with the iron, and you'd form this brown precipitate because of the iron oxide that you form, which is effectively rust. So with this one, you'd form a brown precipitate, and it would give the impression that you'll have a high amount of the titer value would be effectively higher, because you have to add more to it because not all of it's being reduced. So this one's going to be C. Okay, it's quite tricky on that. And then next one. So this is 7. What is the electronic configuration of the stable scandium ion? Right. Well, scandium, the stable ion is Sc3 plus. So if we bring in our periodic table here, you can see there's scandium on this side here. It's got a 3 plus charge, so we lose that electron, we lose that electron, and we lose that electron. So effectively, it doesn't have any s orbital electrons, and it doesn't have any d orbital electrons because we've removed them to form 3 plus, Sc3 plus. So this one is actually going to be D. This is this one at the bottom here. So you can see 3D 0 and 4s 0. Okay, right. On to the next one. So this is question 8. Let's drag that down there. Okay, so it says the shapes of the complexes CrCl4 minus and PtNH3Cl2 are. So this is your platin. This could be cis or trans platinum. We're not sure from the structure of this. So this is your anti-cancer drug. This one is a very classic square planar structure. Chloride complexes like this are tetrahedral. So we're looking for something that is tetrahedral and square planar. So 8 is going to be D. That's just something really you have to try and remember. Okay. And the next one. So question 9. As you can see, there's question 9. So it says the compound 1,2-diaminoethane, which is this compound here, is a bidentate ligand. In formula, it's usually abbreviated to En. When 1,2-diaminoethane is added to this cobalt hexa ammonia complex here, in aqueous solution, you get this complex that's formed. And what is the best explanation for this? Now, whenever you've got a multidentate ligand exchanging ligands with monodentate ligands or unidentate ligands, which are these ones here, what you have is a big entropy change, because you're going from this, which is one complex, to this, and what's missing from here is 6 ammonias that have been displaced. So actually, we have a favourable entropic process, because we're going from something that is has one molecule here with your 1,2-diaminoethanes to this and 6 ammonias. So this one's got 7 in total, as opposed to this one, which you'd only have 4. So that's a positive entropy change, and that's always the case for these. So you can see here the answer here is going to be this one, which is going to be C. Okay, and then 10. So it says when aqueous sodium hydroxide is added to an aqueous solution of a transition metal compound, a green precipitate is formed, which dissolves an excess sodium hydroxide, forming a green solution. The transition metal ion present in the original solution is, right, I'm being pretty crafty here, because we have 3 different compounds here that can actually form green solutions, and we have one which is a complete no-no. So let's get rid of that one first. This one is brown, so there's no green in there whatsoever, so we can get rid of that one. The other ones are green. Now let's have a look at this one. So iron 2, when we this one is green. This is a green solution, and we add a small amount of hydroxide, we form a precipitate. But then when we add excess, the precipitate doesn't go, so it stays as a precipitate. So it can't be that one. It's exactly the same with this one as well, with the nickel one. That's green, but that stays as a precipitate as well. So the only one which is left is chromium. This is green as well, but it will redissolve when you add excess sodium hydroxide and you form a green solution. So that one's really testing your understanding of colours and complexes. Right, on to the next one. Okay, it's question 11. There you go. So question 11 says benzene reacts with a nitrating mixture of concentrated nitric and sulfuric acids. Which species is least likely to be present in the nitrating mixture? So let's write out our equation for this then. So we're going to take our sulfuric acid, which is H2SO4, and we're going to react that with nitric acid, HNO3, and that's going to form, effectively, the nitric acid is going to accept a proton. So we're going to form that, and we're going to form HSO4 minus. There you go. So, well, there's our first one there. So we can effectively get rid of this one because we've actually produced it. We've got some acids here as well. So these acids effectively will produce H3O plus ions, which are effectively acids. So these can dissociate as well and form these. So we can actually discount this one as well. So far we've got 2 immediately discounted. And then this one here, this kind of like intermediate, H2NO3 plus, this actually decomposes and it forms NO2 plus H2O. And so this H2O can accept protons as well, again, to form this H3O plus. And then obviously we've got our NO2 plus. So the one that's least likely is this one here, NO3 minus. So we're just going to put across there. So just a simple, again, it's just trying to understand you, see if you know your equations. That's what the testing on. Okay, and then question 12, it says benzene with a boiling point of 80.1 has a higher boiling temperature than ethanol, which is 78.5. This is because, now obviously we have ethanol's got hydrogen bonding, but this is still a bit higher. Now the only thing that benzene has is actually London forces, and these London forces are quite strong because these are quite flat molecules, remember, so they can really kind of like stack together quite well, and because they can stack together quite well, obviously they've got strong forces, intermolecular forces between them. So what we can say is that obviously the London forces between benzene molecules are stronger. Hydrogen bonds, there is no hydrogen bonds with benzene molecules. we're not talking about breaking bonds here. Boiling point, we're always talking about intermolecular forces, so it can't be D. And the benzene ring is stabilized, has got nothing to do with boiling point whatsoever. So the answer is B. Okay. And then 13. Unlucky for some. It says separate 0.1 moles per dm cubed aqueous solutions of separate, 0.1 moles per dm cubed aqueous solutions of ammonia, methylamine, and phenylamine were prepared. Which of the following sequences shows these solutions in order of increasing pH? Right. So again, what they're assessing you on here is your ability to understand how ammonia is basic, and the idea is that if we have our obviously for a base, bases are effectively proton acceptors. They accept protons, and all these have a lone pair of electrons. Now ammonia can accept a proton pretty readily with its lone pair there. Methylamines though, so this is methylamine, so we'll just put CH3 there. What they do is actually they push electrons in towards this nitrogen, making that lone pair much more readily available. So that means this is going to be much more basic than this. And then the other one is, it said phenylamine. So I'm just going to draw that there. There you go. There's your nitrogen, there's your hydrogen, there's your lone pair of electrons. And you can see actually this has the opposite effect. What this does is pulls electrons away into this benzene ring. So that means this is less readily available. So on that basis, effectively phenylamine is the has the lowest pH because it's the least basic. Ammonia and then methylamine is the next strongest, is the strongest base because it pushes electrons from the methyl group into the nitrogen. So this one's going to be B. Okay, right. On to the next one. So this is question 14. Let's just drag that down there so we can see it. Right, so it says the benzene diazonium ion C6H5 N2+ is an intermediate ion, in the preparation of azo dyes. In the formation of an azo dye, the benzene diazonium ion is right. Okay, so this is basically something that we need to, again, sometimes it just helps to draw these little diagrams. So let's draw that there, and then we have our this molecule here, and this is our benzene diazonium ion, which is this one here, and then effectively we have this coupling reaction, and this forms, there's our phenol, and go, and effectively this will come and react with that, and these couple together. So this is a classic sign of an electrophile because it's a positive charge, and so this is going to attack on there. Certainly not a nucleophile. There's no carbocation in these molecules at all, and it's not a substituent either. It's got nothing to do with it, so this one has to be an electrophile. Okay, and question part B says the temperature of the aqueous reaction mixture must be kept below 10 degrees to prevent the benzene diazonium ion becoming converted into, so this is one you just have to remember, it stops it from forming phenol, so we keep it at a cool temperature. Okay, right, on to the next question. So question 15, this is quite a big question, so let me just see if we can try and get as much of that as we can in the shot there. Okay, so it says the monomer of the addition polymer, polypropanol, may be represented as CH3CH double bond CHOH. The repeat unit of this addition polymer is. Now, what I find with polymers is to try and draw out the molecule with your double bond, but then just branch off whatever you've got here. So I've got, you can see I've just literally zoomed in on that double bond there. And you can see we have a hydrogen and a CH3 coming off one side, and we have a hydrogen and an OH coming off the other. So if I was to open this double bond, this will effectively form this. So we have a carbon there, we have a CH3 there, we have a hydrogen there, single bond, carbon, trailing bond, OH at the top there, and a H. So in terms of a skeletal point of view, this hydrogen will effectively be kind of like ignored, so it would look something like this. So you'd have your two carbons in between, you would have your a CH3, and you'd have your trailing bond, which comes from here, and on this carbon you would have an OH on this side, and then you'd have your trailing bond coming from the other side here. So we have to draw a box there. There's your trailing bond. And there's your trailing bond there. So effectively this molecule, if you look along here, has to be A. And it helps a lot to draw your alkene, draw it like this, then draw it as skeletal. So there's quite a bit going on there. So that one's going to be 15, which is A. Okay, right, so on to the next one. So it says 16. Chromatography may be used to separate mixtures of amino acids. This is best explained by the fact that different amino acids have different interactions with. Now, chromatography, the amino acid is obviously dissolved initially in the mobile phase, which would be the solvent. Then you have a battle effectively between the, well, almost like a battle between the mobile phase, which the amino acid is dissolved in, and the stationary phase, which it's trying to adhere to. So obviously the more soluble your amino acid is, the more time it's going to spend in the mobile phase, and the less time it's going to spend stuck in the stationary phase. So with this one, the interactions are with both the mobile and the stationary phase. That's the case with most chromatographies, to be honest. So this one's going to be C. Okay, the ninhydrin is the chemical that you spray onto it to make the amino acids present, because amino acids are obviously colourless liquids, so it's like a dye, so it's got nothing to do with it really. Okay, and I'm missing a page, skipping ahead of myself. Right, so question 17. So again, it's another quite a big question. It seems like these I'm going to have to move this around a little bit more than I thought. Okay, so just about see that, I think. So there's an aqueous solution with a pH of 7. The amino acid alanine exists mainly as. Now the key thing here is the pH of 7, so this is neutral. And we know it's in solution because that's very, very important. When we have a pH of 7 and this is in solution, we effectively form a zwitterion, which means double ion. It's a German term. So we're looking for a molecule with a positive and a negative. It's not going to be this one. This is if it wasn't. This is if basically if it was solid, it would be this. It's not going to be this one. There's only one negative. There's only one positive in this one, so it has to be D, because that's your zwitterion, and that's what amino acids exist as when they're in solution. Okay, and the last question for section A. It says, when a solid is purified by recrystallization, the procedure involves the removal of impurities by filtration of the hot mixture, followed by filtration of the cold mixture. Which impurities are removed by these two filtrations? Right, so what we need to say is when we dissolve our substance, the substance that we want in hot solution, what we're trying to do is obviously your impurities that are soluble will dissolve in the hot solution. So all your insoluble impurities won't dissolve. So effectively we've got it between these two. And when you do your cold filtration, what happens is all the impurities that were soluble in the hot solution are not soluble in cold solution. So effectively this removes your soluble impurities, so these ones that were soluble with your product. So actually this one is going to be B, and that's something you really have to remember as a how science works aspect. And there we go, you get a nice 20 marks, so it's not too bad for section A. Okay, right, on to section B. Okay, so this is section B, and it says, this is question 19. It says a compound A is known to contain only the elements carbon, hydrogen and oxygen, and was subject to detailed analysis. So we've got a sample of A was burnt completely in the apparatus shown below. Solid X absorbed the water formed in the combustion, and solid Y absorbed the carbon dioxide. So you see here, here's our dry oxygen going in, there's our heat source, and obviously we're going to heat it up and we're going to produce solid X and solid Y and our suction over here. Okay, so this is just drawing it all through. Okay, so we're going to explain why the oxygen must be dry. Well, obviously what we're doing is we're burning this, so this is a combustion reaction, and with any combustion reaction you produce oxygen. So you produce water, so to say, not oxygen. So you produce water. Now, what you want is you just want to measure the amount of water formed from burning your actual from actually combusting your product here. You don't want the water that's coming from the oxygen. So what we have to do is we have to take into account our water, and we have to make sure that the oxygen that we're feeding in hasn't got any water in. So we're just going to put that in there. If you see what I mean, hopefully when I write it you might be able to explain what I mean. So only the mass of water collected in X is from the combustion of sample A. Okay, so you get 1 mark for that. So that's what we mean by that. Okay, so on to the next parts. So let's just do that there. Okay, so it says suggest a suitable substance to use as solid X. So solid X was this first compound here, and solid X absorbed the water. So we're looking for something that will absorb water, and typically we're looking for things like anhydrous, which just means dry with no water. Calcium chloride is a good one. Calcium chloride. Or you could say something like magnesium sulfate. So I'll just write the formulas there for time. So magnesium sulfate. Or you could use sodium sulfate as well. Not nitrogen, what we're doing. Na2SO4 sodium sulfate. There you go. Okay, so any one of them will do really, and you get your mark. And it says suggest a suitable substance to use as solid Y. Now solid Y is absorbing the carbon dioxide. So your substance, remember this is a solid, so your substance could be something like calcium hydroxide. You can't say lime water because lime water is a liquid. So I bet that's a lot of people probably would have put that. Calcium hydroxide and sodium hydroxide. Or you could say soda lime, which is your solid. So yeah, that's a really tricky one. Again, read it really carefully because a lot of people would have gone for, I would imagine, would have gone for lime water, but it is suggesting solid. So you have to give a solid form that would detect the carbon dioxide. Okay, right, so on to the next part. This is quite a big question. It says 3.6 grams of compound A was burnt completely. The mass of solid X increased by 3.60 grams and the mass of solid Y increased by 8.80 grams. Use these data to calculate the empirical formula of compound A, and you must show you're working. Right, so what we need to do is we need to work out the masses of carbon, hydrogen, and oxygen. Now we have compounds that contain our carbon and our compounds that contain our hydrogen and obviously our oxygen as well. Remember, we're producing carbon dioxide and water. So I'm going to start with let's start with the carbon one first. So we know the carbon dioxide formula, and we know that we produced, it increased by 8.8 grams, which is on there. And to work out this, we need to work out the number of moles. So we take our 8.8 and we're going to divide it by 44, because that's the molecular mass of carbon dioxide if we use our periodic table. So if we bring in our calculator, so we're going to do 8.8 and we're going to divide that by 44, and we should get 0.2. Okay, and what this is telling us is basically this is the number of moles, but this is also telling us the number of moles of carbon. So I'm just going to put carbon there. Okay, so that's our first one there. Also, we've also got water as well, and the water can tell us the number of moles of hydrogen because it's the only molecule with hydrogen in. So again, we produced an increased mass of 3.6 grams, and we're going to divide that by the molecular mass of water as 18. Again, you work that out from the periodic table. So oxygen 16 and then 2 hydrogens and 1, so that's 18. Put that in our calculator. So, and we're going to put in 3.6. We're going to divide that by 18. We're going to get 0.2 as well. Right, now the problem is that's fine, but that is the number of moles of water. So to find out the number of moles of hydrogen in the water, we need to double it because we've got 2 hydrogens in there. So we need to take this number and we're going to multiply that by 2, and we don't really need a calculator for that one. That's 0.4, and that's going to tell us the number of moles of hydrogen in there. Now, onto the mass of oxygen, or the number of moles of oxygen, should we say? And what we need to do is we need to work out the mass of oxygen that is left behind. So, in order to do that, we need to subtract the masses of our carbons and our hydrogens and see what mass is left. So, so what we're going to do is we're going to take our 3.6 grams with the mass of solid Y. So we're going to put in there 3.6, and we're going to subtract that away from the mass of carbon, which is 12 times by the number of moles. Remember, that's the MR of carbon. The number of moles is 0.2. Okay, we're going to add that to the mass of 1 times 0.4. We're going to add, so we're going to add like both of these together, and then we should get a mass. So let's work this out. So let's do the 12 times by the 0.2. Let's work these out separately. So that's going to be 2.4. Obviously, that's going to be plus 0.4. So if we add them up together, that's going to give us 2.8. So we've got 3.6 minus 2.8. So 3.6 minus 2.8 is 0.8. Right, and so that tells us the mass of our oxygen. So we'll put O on there. Obviously, we need to work out the number of moles. So the number of moles is mass over MR. So the mass is 0.8 grams divided by the MR of oxygen, which is 16. And then this should tell us the number of moles of oxygen that we have in our as our product. So we have 0.8, divide that by 16. That's 0.05. Alright, so now what we have is the number of moles for carbon, the number of moles for hydrogen, and the number of moles of oxygen. And what we do is we need to get that into some kind of empirical formula. So let's nudge that up a little bit. So a neat little way, I suppose, of doing this, I'm just going to put our headings up there. Carbon, hydrogen, oxygen, is to take the number of moles and divide each of them by the lowest number of moles. So the lowest number of moles here is this one. So we're going to divide all the numbers by this. So if we do 0.2 divided by 0.05, and we've got 0.4 divided by 0.05, and then we've obviously got 0.05 divided by 0.05. The reason why we do this is because you always have one that's 1. So that one's always a 1 ratio, which is that one there. And then we're going to work out these ones here. Bringing our calculator back again. So it's going to be 0.4 divided by 0.05, and that's going to give us a ratio of 8. So you can see on there, I'm just going to put 8 underneath there. And then our next one is going to be 0.2 divided by 0.05, press the equals, we get 4. So that one's going to be 4, which goes in there. So our empirical formula is going to be C4H8O. There you go. And that's our final answer. So 5 marks for that. So it's quite a decent number of marks. The marks come in basically for working out the number of moles of carbon to be 0.1. You get 1 for working out the number of moles of hydrogen to be 0.4. You get 1 for working out the mass of oxygen to be 0.8, and then hence working out the number of moles as a result. And then obviously you get 1 for your final answer, which is that one there. So you get 1, 2, 3, 4, 5 marks for that. So yeah, pretty substantial number of marks. Not too bad. Okay, right. So on to the next part. Right, and this is showing us the mass spectrum of A is shown below. Identify the molecular ion peak and hence deduce the molecular formula of A. This is pretty straightforward, to be honest. Molecular ion peak is the most significant peak furthest right on your mass spectra. So in this case, it's going to be this one here. That's going to give us an ME of, or molecular mass, of 72. And lo and behold, if we take the formula that we had here before, this one here, our empirical formula, if we add up this, that's obviously carbon's 12, that's 1, and that's 16. If we add them up, then we should get a mass of 72. So actually its empirical formula is also its molecular formula. If that number was obviously doubled, like 144, then you would suspect that you would double all of these. So you would do C8H16O2. But in this case, it's not. It's the mass of 72. So therefore, the formula is actually going to be, let's put that there. So the formula is actually going to be C4H8O. And you get 2 marks for that. You get 1 mark for deducing your molecular ion peak, and then 1 mark for your formula as well. So you get 2 marks in total. Okay, right on to the next section. The next part of the question, should I say? Okay, so we have part 2. It says, given that A does not have a ring structure, suggest the structural formula of 3 of the species that might cause a peak at Me43 in the mass spectrum of A. Right. So we're looking for basically fragments or bits of this molecule that we can break. And the bonds that we're breaking, remember, are the CC bonds. They're the ones which are the weakest ones. So we're looking for fragments where we're breaking this CC bond. I'm going to write down all the different fragments. You only need 3 of them. There's 6 different fragments that you can pick that all add up to 43. So these fragments are going to be H3C, CH2, CH2 plus. So there's 1. All of these must have a positive charge as well. That's another thing. Let me just write this one down. So all of them actually have a positive charge because the mass spectrometer needs a positive charge to accelerate the ions through the mass spectrometer. So they must all have positive ion fragments. We could have H3C, C double bond O, nice carbonyl group there. We could have H2C, C, H double bond O. We could have H2C double bond C positive OH. Or we could have a terminal carbocation as well. Okay, so you could have anything like this. CHOH. There we go. So 3 marks. You only need 3 of them. I've drawn all 6 of the different fragments there. They all add up to an ME of 43. So any of them would get you obviously all the 3 marks there. Okay, and then on to the last part. Let's just nudge that up there. There we go. So it says the low resolution NMR spectrum of A has 3 peaks in the ratio of 6 to 1 to 1. Draw the structure of A and show how your structure is consistent with the NMR data. Okay, so right, when we see a ratio like this and we see a 6, what this means is that we have well, first of all, we've got three parts here. So we have 3 proton environments. So that's the first thing. But one of these proton environments, and we have 6 hydrogens in the same environment. When we see this, you need to immediately think of something like this. Sometimes you might see the number 9 as well. If it's a 9 there, then you'd have another CH3 coming off here. And basically, these CH3s are all attached to the same carbon. So they're all in the same environment. But that's really what you're looking for. It's a big clue, and it uses up a lot of atoms as well, so helps form your structure properly. So actually this 6 is because of this here. Obviously we have another hydrogen environment there. This is a singlet, so we have a peak of 1. So there's a hydrogen there. That's a separate environment to these ones, because these are attached to a carbon first, which are then attached to this carbon. This one's directly attached to that carbon there. And then we have obviously another carbon, hydrogen. There's an other environment there, and then our double bond oxygen. And you've got to make sure that the this structure here matches the molecular mass of your original molecule, which remember we said was 72. We said the actual molecular mass of this thing as well was C4H8O. So we need to make sure that we've got the right number of carbons, the right number of hydrogens, 6, 7, 8, and the oxygen as well there. So it must match that. That's the key thing. And that's how you work it out. You mustn't have more carbons or less carbons or less atoms, should I say, for that matter. So there's our structure, and we just need to add a little bit of commentary as well, basically what I said before. So we have 3 proton environments. We have 6 protons in one environment, and we have 1 in each of the other 2. So basically what we've done is we've just described our structure here. So you can see we've got obviously 1 for this, for our actual structure, 1 for 3 proton environments, and then 1 for the final bit there. So we get 3 marks in total. So there you go, not too bad. On to question 20. Okay, so this is question 20. Question 20 starts with ibuprofen, which is that wonder drug that takes away them headaches. So it says ibuprofen is a non-steroidal anti-inflammatory drug or an NSAID, widely used as an analgesic, which is a pain reliever. It was discovered in the 1960s by the Boots Group, which developed a 6-step synthesis from 2-methylpropylbenzene, and the synthesis shown below was introduced in the 1960s by the BHC company and received a Presidential Green Chemistry Challenge Award in 1997. So that's pretty good. And says the citation noted that the synthesis has just 3 steps, all of which are catalytic, and an effective atom economy of 99%, which is really reasonably good. And it says both syntheses are carried out in solution. So we've got all this synthesis here. I'm just going to ask us questions about it. Okay, so the first question, it says suggest why a 3-step synthesis is likely to be greener than a 6-step process. Well, I suppose the obvious thing is that because we've got less steps, we're going to have less waste products overall, and we're going to have a higher yield as well. So we're just going to put that in there. So less waste products, and so therefore what we're going to have is we're going to have an overall higher yield, because obviously the more steps we have, if we're transferring from one beaker to another, if we have doing that 6 times over, we're going to be losing products. So the least steps we can do it in, obviously the better. We're not losing as much of our valuable chemical. Okay, so the next one. So it says, why does the use of catalysts make processes greener as well as faster? And the whole point of a catalyst is obviously to provide an alternative pathway for reaction to occur. But catalysts are also really useful in that they lower the temperature required. If you lower the temperature, you're not using as much fuel. So therefore, it's obviously a greener alternative to not having a catalyst in there. So let's put that in there. So lowers the temperature required. All right. Okay, so we get 2 marks for that. Not too bad. Okay. On to the next part, part B. So part B says the first step of the synthesis is an electrophilic substitution, which is usually carried out in a school laboratory using ethanol chloride and an aluminium chloride catalyst. Write an equation showing the formation of the electrophile in the school experiment. Right, so this is our acid chloride. And they've said it's ethanol chloride. So the formula for ethanol chloride is CH3COCl. Okay, it's pretty nasty stuff, this stuff. AlCl3. And we're going to form, effectively what's going to happen, this is called a halogen carrier. It's basically going to carry the halogen from the chlorine. And what's left behind is CH3CO. We have a positive charge on there. And we have AlCl4 minus. It's carrying the halogen from there to form your electrophile, which is this molecule here. Okay, and then the next question, it says give the mechanism for the electrophilic substitution of 2-methylpropylbenzene by ethanol chloride using the electrophile you've given in B part 1. Okay, so we're going to draw, let's just nudge that up there. So we've got a decent amount of space. Okay, so what we're going to draw is we're going to draw our obviously our molecule. So we have our benzene ring, and this is the molecule that was given to you right at the start. We're going to put our electrophile here. Right, and so then what we have to do is basically we've got a positive charge here. Here's the electrons, loads of electrons, high electron density in the benzene. It goes onto that delta positive carbon. It must be drawn towards the carbon, not to a bond or not to anywhere else. So be really specific with your diagrams. We're then going to draw our benzene molecule over here. And there's this bit. And then what we've done is we've now added on here this bit here, and we've still got our hydrogen on there. That's a mistake. That should be a horseshoe shape, not a benzene ring. You shouldn't have a ring in there. Okay, that's my fault. So it should be a horseshoe shape, because what you've done is you've distorted the electrons in the middle here. You've pushed them away from this carbon here, so your ring can't be complete here. It must be separated, and try not to draw it beyond these carbons here. But yeah, it certainly mustn't go there, and the horseshoe shape must point towards this carbon here as well, so make sure it's drawn exactly like that. You do have a positive charge in the middle there as well, because you've got a deficiency of electrons in the middle. Then what we need to do, and that is very important, that diagram actually, because that is a marking point. Then the electrons from this bond here go in to stabilize this positive charge. Effectively, we want to cleave this bond, we want to get rid of it. So we're now going to draw our final product. Now we do have the benzene delocalized structure reformed, and the hydrogen from here has now gone, and we must draw it down here, H+, and there we go. Okay, so let's divvy up the marks. We've got 3 marks here, so again, not bad for a mechanism. So we get 1 mark for drawing, obviously, this arrow here. We get 1 mark for the intermediate. That's a positive charge in the middle there with a horseshoe shape facing that way. 1 mark for the arrow. And there's your 3 marks, and obviously there's your final product there at the end there. Okay, right. On to the next part. So it says, suggest one environmental benefit of using CH3CO2O rather than ethanol chloride. So this is an acid anhydride, this molecule here, and the main reason is actually the fact that with acid chlorides you get HCl gas being produced, hydrogen chloride gas, which is really horrible stuff, and using this you don't get any HCl being formed. So the idea is that you just need to say no HCl formed. Okay, so you get 1 mark for that. Alright, on to the next part. Part C. There you go, just dragging it down. So it says the final stage of the modern synthesis for ibuprofen is shown below, and you can see we've got it here. State the benefit of using a solid catalyst in this reaction. Solid catalysts are good because we can remove them at the end of the reaction. We can take them out quite easily, so that's what we need to put them there. So catalyst easily removed via filtration. There we go. And there's your mark. And that's the case with all solid catalysts as well. They're pretty easy to remove. Okay, right, on to the next part. Right, so we've got a series of different reactions here. So we've got the preparation in part C. Remember, it was that last part. Can be carried out in a laboratory in 3 reactions. And you can see we've got 3 different reactions here. Give the reagents for, there we go, that's the question there. So it says give the reagents for reaction 1. So let's pull that down there. You can see here that we're going from an OH to an iodine molecule. So we can either use phosphorus and iodine, or an iodine on the end, or we can use HI. So any of them will do. So let's put that on there. So let's put phosphorus and iodine. Or you can use hydrogen iodide as well, which is HI. Cool. Okay. And then on to the next bit. It says the reagents and conditions for reaction 3. So the reagents that we require for reaction 3, which is this one here, is basically this is just the reagents. So we're looking for something like HCl or sulfuric acid. So acidic conditions, anything or a comment on acidic conditions. And reflux as well, because these are quite volatile chemicals, so most of the time we're using reflux for volatile chemicals. It's 3 marks. You actually get 1 mark for this answer here, and obviously you get 1 for this for saying acidic conditions, and 1 for saying reflux. You get 2 there. So again, not too bad. Okay, on to the next part. It's quite a big question, this. Okay, there's certainly a lot of pages. So part 3, using your data booklet, explain how infrared spectroscopy can be used to distinguish between the 2 structures shown below. Okay, right, so I suppose the key thing here we're looking for is key differences, and the biggest difference is this, look. We've got a carbonyl group there, and it's actually part of a carboxylic acid. So if we bring our, you have this massive data book, which is here, okay, and you can see we've got our infrared data here. Now the carbonyl group, this is your carboxylic acid there, it's your alkyl group. This has a wave number of 1725 and 1700. Now your other group, the other molecule with the OH, just with the OH in, won't have that peak. So let's just pull it out of the way. This one doesn't have a carbonyl, so therefore what we can say is we can say the C double bond O group in ibuprofen. That's the main difference. And what we're looking for in an infrared is we would actually get an absorption. At 17250, 1725, sorry, wasn't it? Yeah, to 1700. Now you wouldn't see that with the other molecule. You wouldn't see that with this one here. So you need, first of all, identify that there is difference, what the difference is, and then say, well, what would you see on your infrared spectra? So you'd see them too. So you get 2 marks for that. So we get 1 for this and 1 for this. Okay, and then part B. Says ibuprofen is a chiral molecule and only one of its enantiomers is biologically active. However, although the synthesis produces a racemic mixture, an isomerase enzyme in the body converts the inactive enantiomer into the active enantiomer. So that's quite handy. So we need to explain the term chiral molecule. Okay, so the molecule that is chiral is basically something which is non-superimposable on its mirror image. So, for example, I could take my hands, there, and you can see they are non-superimposable. It doesn't matter how many ways I actually do it, and they're not going to actually superimpose on top of each other. So, let's say that my hands are actually chiral. We can say the same with molecules as well. And so, molecules which are chiral are non-superimposable on its mirror image. So, let's write the answer down in there. So what we could say is you can get 4 different groups around the carbon atom, because that's what you're looking for. Is you're looking for in a carbon atom in the middle, you're looking for effectively 4 different groups that's coming from that carbon there. But these are non-superimposable, so that's the key thing. So any one of them answers will do. And then the next bit, it says mark with an asterisk the chiral center on the structure of ibuprofen below. So there is one chiral center on here, and we're looking for carbon with 4 different groups. This is the carbon here. Let me just explain why. You can see we've got a carbon here. We've got a methyl group there. We have this carboxylic acid group here, this carboxyl group here on the end here. And we have a hydrogen there, but they don't draw on skeletal. And then we have this, obviously, all the rest of the molecule here. They are 4 different groups, so therefore this is the chiral center. This isn't here because we have a double bond oxygen. Yes, we have an OH, and we have an O, and then we have the rest of the molecule. Because we have a double bond, that isn't chiral, so don't be tempted to mark that one. Okay, right. So on to the next bit. Right. So it then says, explain the term racemic mixture. So a racemic mixture is basically an equal amount of 2 enantiomers. So that's just something you have to remember, really. Or you can put equimolar or anything like that. That'll do. So equal amounts of 2 enantiomers. Or you could say something like a 50-50 mix. Anything that will do, really. It's just one mark, but yeah, you've got to say it's an equal. Equals an important bit, and the enantiomers is obviously key there as well. So make sure you include them words. Okay, and then finally onto IVs. It seems like a huge question. So it says suggest 2 benefits that arise from the isomerization of the inactive enantiomer of ibuprofen. Right now. Obviously, we just need to suggest 2 here, but the good thing is because obviously we have the useful enantiomer anyway, and we have the enantiomer which isn't any use in the body, but the body can change that into a useful molecule, so that's quite good because that means that all the ibuprofen is now useful effectively. It doesn't matter which enantiomer you put in, so that's really good. So we'll put all ibuprofen is useful. And also, I suppose you could say that we don't need to separate these enantiomers. It's very expensive to separate enantiomers from a medicine. So if we can keep them in and not remove them, surely that's got to be quite good because it means the drug's cheaper for people to buy. So another point I suppose you could say is that we don't need to separate the enantiomers. Okay, and I suppose you could also say because obviously just one small dose of the ibuprofen has both enantiomers in, and both enantiomers are useful, then we don't need large tablets, and a smaller dose could be used as well. Because remember, if you've got a tablet and half of it is effectively a useless enantiomer, then you need to compensate by adding double the amount to make sure you've got the right amount of the useful enantiomer. But if the other one, if both enantiomers can be useful, well then you don't need to add double the amount in. Yeah, so you've got to be aware of that as well. So you get 2 marks for that. So it's not too bad, is it really? So you get 1 there and a 1 there as well. Okay, so you get 20 marks for this question. So on to question 21. Okay, so this is question 21. And question 21 starts off by saying the following method was used to estimate the concentration of ethanol in an aqueous solution Q prepared by the fermentation of sucrose. So obviously we're producing ethanol here, and it says 25 centimeters cubed of Q was measured using a pipette and transferred into a 250 centimeter cubed volumetric flask. So we're putting it into a larger flask, and the flask was made up to the mark with distilled water and mixed thoroughly, forming a diluted solution R. Right, so we've got a lot of letters here. So then what we did was then took the 25 centimeter cubed samples of R, that was the diluted solution, were mixed with an equal volume of a 0.200 moles per decimeter cubed potassium dichromate solution and excess dilute sulfuric acid. So we took the 25 centimeter sample from our big container, put it into a smaller container, and added some of this dichromate and acidified it as well. That's what the sulfuric acid's there for. So don't worry too much about that. Okay, and then it says the mixture is allowed to stand for several hours. And then the amount of unreacted potassium dichromate was determined by titration against a 0.255 mole dm cubed iron 2 ammonium sulfate solution. So we've obviously titrated it in the burette. We're going to have our iron compound, and then our reaction that we let to sit for several hours. We're then titrating that solution we left to sit with this, and we're basically just trying to work out how much potassium dichromate do we have left in our conical flask. So, and we worked out that actually the mean titer was 23.85 centimeters cubed. Okay, so we're going to use the ionic half equations below to write the full ionic equation for the reaction between potassium dichromate and the iron 2 ammonium sulfate. So this is basically what's happening in our titration. So they've been very kind to us. They've given us the equations here, which is very nice of EDEXCEL. And you can see, let's just nudge it up so we get some space. You can see that we have our iron 3 going to iron 2. Now, the question here says that we're actually adding iron 2, I think. There it is, yeah. So we're actually titrating iron 2. And obviously, as a result, we're going to form iron 3. So this equation, firstly, needs to be swapped around the other way round. So effectively, let's just swap that around. Because that's the first thing. You've got to really watch out for that, because the Fe2 is what we're adding to it. We're not forming Fe2, we're reacting with it. And the next thing, you can see we've got 6 electrons here. When we're forming a full ionic equation, we need to make sure the electrons are balanced first. You can see we've got 6 electrons here, so we need 6 there. And so everything in that equation is going to be multiplied by 6 as well. Okay, so let's write out our equation. So we've got, effectively, let's take our dichromate. So this is going to be Cr2O72 minus. That's going to act with, that was the acid that I said we added in. This is just to acidify it, really, sulfuric acid. It's obviously important, but you don't need to worry too much about it. The electrons cancel out. Let's get rid of them. And we've got 6 Fe3 plus. Nope, Fe2 plus. Nearly fell in that trap. So this is what we're reacting. We're titrating this against this. This is in the conical flask with this. This is all acidified. And this is in our burette. That's what we're going to add. So, and then obviously we're going to form 6 Fe3 plus. We're also going to form our, obviously, 2Cr3 plus 7H2O. And there we go. So there's our equation. Now this is going to be really useful when we do our titration calculation. So we'll come back to this. Right. And the next one. So it says calculate the number of moles of potassium dichromate that remained unreacted after standing for several hours with solution R. Right, now this is where our equation comes in, actually, ironically. So what we're going to do is we're going to work out the number of moles of Fe2+. Because remember, we know a volume of this is our mean titer. We know the volume of this, and we know the concentration of this. So if we can work this out, we can work out the number of moles of Fe2+. And then once we work out the number of moles of Fe2+, we can then work out the number of moles of dichromate. And remember, we were working out, we're determining the amount of unreacted, there you go. So the amount of unreacted potassium dichromate was determined. So they've told us actually what we're doing. You just have to read the question, I suppose. So right, let's write it down. So we've got moles of Fe2+. There we go. So the moles is going to be concentration times volume. I'm just going to do the other way around. Why not? So it's volume is 23.85. That has been decimeters cubed, so I'm going to just stick that in the end there. That's the same as divide by 1,000. And we're going to multiply that by the concentration, which is 0.255. Okay, right. Let's stick that into our calculator. So let's bring that in here. So we're going to put in here 23.85 times by 10 to the minus 3. And we're going to multiply that by 0.255. Bang. There you go. And there's our answer. So we get 6.08175 times by 10 to the minus 3. I'm just going to write the whole thing down because it just helps with our precision, really. So 6.08175 times by 10 to the minus 3. and that's going to be moles. So now we know the number of moles of iron. This is a good saying really when you're doing these. If in doubt, work out the moles. If you work out the moles of one thing, you can work out the moles of anything else in this equation. So because we have a volume and a concentration, then why not? Let's do it. And then obviously now we do that, we can then work out the number of moles. The moles of unreacted dichromate, Cr2O7, 2 minus. And that's going to be dead easy. We're just taking this number, which is the number of moles of our iron times by 10 to the minus 3. Divide that by 6, because we have a 6 to 1 ratio. There, 6 to 1. So we divide it by 6, and that should tell us the number of moles of our dichromate. Alright, so let's just put that over there. Okay, so this is going to be 6.08175 times by 10 to the minus 3. We're going to divide that by 6. Bang. And there's our answer. So it's 1.013625 times by 10 to the minus 3. Okay, and this is going to be moles. There we go. So there's our first 2 marks. So not too bad. Okay, so we're going to put 1 there and 1 there. Okay, cool. Right, so we know the number of moles of dichromate now that's unreacted in our burette. Or atomic flash, let's say. Right. Okay. Part 3. Right, let's drag this down. Right. Okay, so we've got to calculate the number of moles of potassium dichromate that reacted with ethanol while standing for several hours with solution R. Right. Well, I mean, what we have to do is we have to work out the number of moles of the dichromate right at the start, and then we just subtract it away from the number of moles that actually reacted, and then we'll work out how many moles we have left. So let's quickly work that out then. So we're going to look in here. We're looking for the number of moles right at the start. We had a 25 centimeters cubed sample originally, and the concentration was 0.2. So we're going to use these numbers here to work out the number of moles of the dichromate initially, before the reaction happened. Okay, because obviously if we're going to work out what's left, we have to work out what we had at the start first. So we're going to put moles at the start. Let's put start. Okay, and that's going to be 25 times by 10 to the minus 3. That's the volume that we added. And we're going to multiply that by the concentration, which told us in the question. 0.200 equals, calculator in. Okay, 25 times by 10 to the minus 3. Multiply that by 0.200. There you go. 5 times 10 to the minus 3. Okay, and this is the number of moles. Remember, this was at the start. Now, what we need to do is we need to take this number and we need to subtract it away from the number of moles of dichromate that we had after the reaction. And as if by magic, we worked that out in the previous question. That's how much we had, because that's what we worked out. So how much remained unreacted. So we're going to subtract that away from that, and then we'll work out, obviously, how many moles of potassium dichromate actually did react with the ethanol, because this is what we had left over that didn't react. So obviously, if we subtract the original number from this number, we'll find out how much did react, if you catch where I'm coming from. Okay, so let's do that. So we're going to put, let's put moles that reacted. All right, okay, so the moles that reacted is going to be this number here, 5 times by 10 to the minus 3. That's how much we had at the start. And we're going to subtract it away from our previous number, which was, I think we've written it down here, yeah, which is 1.013625 times by 10 to the minus 3. Go. Stick that in a calculator, lots of calculation, love it. Okay, right, so 5 times by 10 to the minus 3, and we're going to subtract that away from 1.013625 times by 10 to the minus 3, and there's our final answer there. So we've got 3.986375 times by 10 to the minus 3. So let's just write that whole number down as well. 3.986375 times by 10 to the minus 3. Okay, and this is the number of moles that actually reacted. So there's our first bit. So we get 2 marks for that as well. So you get obviously 1 mark for that answer and 1 mark for that answer. Okay, right. So on to the next question. So it says, write an ionic half equation for the oxidation of ethanol to ethanoic acid. Use your equation and the half equation for the reduction of dichromate ions to show that 3 moles of ethanol are oxidized by 2 moles of potassium dichromate. Right, so what we need to do is write our obviously our equation for the alcohol bit. So we're going to write our ethanol, which is going to be over here. So ethanol is CH3 CH2OH, and that is obviously going to form our carboxylic acid, which is CH3COOH. Right, and a way in which we can balance this, which I quite like to do, is actually to start with water first, and water is there to balance your oxygen. So you can see that the number of oxygens here is 2, number of oxygens here is 1. So I'm just going to add water on this side, H2O. And then we're going to add protons to balance out hydrogens. You can see here that we've got 3, 4, 5, 6. We've got 6 hydrogens there and 8 hydrogens in total on this side. And on this side we've only got 4. So actually over here we need 4H plus on that side. And then we use electrons to balance charges. So you can see we've got a 4 plus overall on this side, neutral on that side. So we're going to add 4 electrons on that side. Okay, so there's our first equation. And then it asks us to show that the 3 moles of ethanol are oxidized by 2 moles of potassium dichromate. So what we're going to do is add our dichromate equation in here. I think it makes it a little bit clearer to see. So Cr2O7 2 minus, and we're going to react that with 14H plus. And 6 electrons. This is the equation that we had last time. So you don't even need to work this one out. Oops, capital C. Cr3 plus 7H2O. Alright, okay, cool. Right, so there's our equation. Now the first thing we need to do really is we need to try and make, and I'll get a different kind of pen, we need to try and make the electrons balance out here. You can see that we've got 4 electrons here and 6 here. To make these balance out and then work out the number of moles that react with each. So what we need to say is to get these to be the same, I need to double this one and need to multiply this equation by 3. And what that means is it means I get the electrons to be the same on the top and the bottom. So we double all of this, so we put 2, this is now going to be 28 H plus, this is now going to be a 12, this is now going to be a 4, this is now going to be a 14. And then this one's multiplied by 3, 3, 3, 3, that's going to be 12, and this is going to be 12 as well. And then what we can do is effectively now we can cancel out our electrons. But what you can see here now is effectively the 2 dichromate molecules will now react with 3 molecules of ethanol. You can see there's the ratio there. So effectively by doing that, we've effectively demonstrated using the equation what's happened. So let's write this down in words though, because they love words. So 3 mole of ethanol needs 12 moles of electrons supplied by 2 moles of potassium dichromate. Running out of space there. Go. All right, so yeah, so basically what we've got is you've got 3 moles of your ethanol, which is here. These need 12 moles of electrons, as you can see here. There's your 12 moles of electrons supplied by 2 moles of potassium dichromate, which is this one here. So this is effectively going to produce them to allow this to reduce. So yeah, comment on the electrons. The reason why we balance these out because we need the 12 electrons for it to do that, and so that's how we've done it there. So you get 2 marks for that one. You get 1 mark obviously for your description. Let's bring my red pen. So we get 1 mark for our description there, and we also get 1 mark for actually writing our equation initially at the top there. So there you go. So you get 2 marks. Okay, right, on to the next part. Right, let's just bring that into shot. So it says calculate the concentration of ethanol in moles per dm cubed in solution Q. Right, well the first thing we need to do is to work out the number of moles of ethanol that did react with the potassium dichromate. So yeah, okay, so what we need to do is we need to go back to part 3 really, and we need to work out actually how many moles did react with the ethanol. So let's just write this down here. So moles of ethanol that reacted with K2 Cr2O7. Right, well, the number of moles that reacted is going to be the number of moles of dichromate that reacted as well. And so that number that we used there was this one here, because remember we're doing a titration, so this would be the same number of moles. So this would be the number of moles that actually reacted. So let's write that down there first. Let's just drag that up there. We'll need that equation actually, so we'll keep that there. Okay, so we're just going to put that there, 3.986375 times by 10 to the minus 3. Okay, now what we need to do is we need to actually work out the number of moles of ethanol. So we've got the number of moles of dichromate, which we had here. This is the number that we worked out in the previous question. This one here, that was the number of moles of dichromate. So what we're going to do is we're going to effectively, we're going to divide that by 2. First, and then we're going to multiply it by 3 to work out the number of moles of ethanol that actually reacted, because remember these two will react together in this 3:2 ratio. So divide by 2 to find 1 mole, and then multiply it by 3 to get that. So that's the thinking behind this. Right. So let's just bring in our calculator. Right. So we're going to do 3.986 375 times by 10 to the minus 3. Divide that by 2. And you can see that we get a number which is 1.9931875, and that's going to be times by 10 to the minus 3. Okay, and so that's the number of moles. And then what we're going to do is they're going to multiply that by 3. So take that number times that one by 3. Okay, and then we're going to get that number, which is 5.9795625 times by 10 to the minus 3. Okay, so this is the number of moles of ethanol that reacted with the dichromate. That's that answer there. Right, now it didn't want that. Remember, this is just the number of moles that we had in our conical flask. So there's our, let's draw a quick conical flask. Okay, and we had our burette. Okay, so there it is, and we had 25 in there, 25 centimeters cubed. Right, but remember this was formed from a diluted solution. So we actually need to upscale this. The original amount, remember at the start, we said we took a very concentrated amount, added it to a 250 centimeter cube flask, and then we diluted it down. So obviously we've diluted it down and then taken a portion of that, 25 centimeters cubed, and then put it into here and then titrated it. So effectively what we have to do is work out the concentrated amount. So the moles in 25 centimeters cubed of Q. Remember Q was the, if we come back onto this, so Q was the actual original concentrated solution that we had before we diluted it to make R. So to do that, this is the tricky bit. Now to do that, we need to, and I'll just write it over here just to make it really clear. So moles in 25 centimeters cubed of Q. Remember, this is the original amount. We need to take this number of moles, which is the diluted one, and times it by 10. because we are multiplying it by a factor of 10. Remember, this was a tenth. This 25 centimeter cube portion down here, this one here, this 25 centimeter cube portion was a tenth of the diluted solution. So to work out what it was for the whole amount, we just need to multiply it by 10. So we're just going to put that there, 5.9795 where are we, 65 times by 10 to the minus 3, multiply that by 10. Okay, and so that's obviously going to be 5.979565 times by 10 to the minus 2. So that's pretty straightforward. Okay, so that's the number of moles and 25 centimeters cube of Q. So this was the original amount, remember. Okay, so then all we have to do is then we need to work out the concentration. So that's moles. And this is relatively straightforward. So let's just write this down here. This is 5.97 ... whatever that is effectively, this is in 25 centimeters cubed, because that was the original solution. So what we need to do is, that's no good, we need to work it out in a decimeter cubed. So decimeter cubed is 1,000 centimeters cubed. So to get from here to here, we have to multiply that by 40. So we take this number here, which is this bit, I've just paraphrased it, and we're going to multiply that by 40. I'm only doing this just to kind of illustrate where we're going with this. So we're going to take this number here, multiply it by 40, and this will tell us obviously in moles per decimeters cubed how many it is, because at the minute this number is moles per 25 centimeter cubed, which is not what we want, moles per decimeters cubed. So we're going to multiply it by 40. So we're going to take that number there, 5.979565 times by 10 to the minus 2, and we're going to multiply that one by 40, and we should get 2.39 there, and that's going to be your answer. I'll just write over here, 2.39, and that's moles per decimeters cubed. So that was the original concentration of the original solution that we had. Because remember, we took a really concentrated solution. It's like taking orange juice. So imagine you've got some orange squash, and you take the orange squash and you put it into a jug. That's like your big solution, your big your 250 centimeter cube flask. So we take the orange squash, we put it into the jug, and we then add water, dilute it down. We then take a portion of that diluted juice, and then we put it into a glass, and then you drink it. This is effectively like the same thing. We start with a concentrated solution, we added it to 250 centimeter cube flask, diluted it, we measured 25 centimeters cubed of that diluted solution, and then put it into there. So it is the kind of like same way. So we get 3 marks. That's quite a tough question, that one. You really do need to know your moles for that one, really. You get 1 mark for working out, obviously, your this bit, number of moles of ethanol that reacted with the dichromate. You get 1 mark for working out your number of moles, this bit here, and you get 1 mark for your final answer. So you get 3 marks there. So yeah, decent number of marks, but a lot of work. Okay, and then on to the next bit. So this is B. Alright, okay, so it says the indicator used in this titration was barium diphenylamine sulfonate. Wow. Okay, so this turns from deep purple to colourless at the end point. Identify the ion responsible for turning the indicator from deep purple to colourless at the end point. By considering the type of reaction involved when this ion reacts with barium diphenylamine sulfonate, suggest how barium diphenylamine sulfonate acts as an indicator in this titration. Note that complex formation does not occur, and the detailed reactions of this particular indicator are not required. Okay, right. Thank the Lord for that. Right, so the obviously what this is reacting with is it's reacting with the iron 2+ ions that are in your solution. So let's put that on there. So put Fe2+. That's the ion responsible. And then obviously what we have to say is what type of indicator is this? Well, the type of indicator, this is a redox reaction. So that's the type of indicator it is. It's not. This is not an acid-base reaction. And you may think it because it's a titration. You think, well, normally it's an acid-base, but this one isn't. This is a redox one. So how do you spell this? Okay, so diphenylamine sulfonate is a redox indicator, so it's not an acid-base indicator. All right, and then what we need to say is the barium diphenylamine sulfonate is effectively reduced by the Fe2+, because remember this Fe2+ is oxidized, so this obviously the indicator itself must be reduced. It's a redox reaction, so we'll put that on there. All right. Okay. So we get 2 marks for this. 3 marks. Sorry, not 2. Cut your mark short. We obviously need to say the 1 mark is for the identification of the ion that this indicator will react with. Then we need to say what type of indicator it is, and then we need to just briefly describe what the indicator is doing. And indicators change color because they are reacting with the chemicals in your solution, so they are changing color. Now, in this case, it's obviously monitoring how much Fe2+ there is, and once this has run out, then the indicator will obviously will go colorless, and so therefore there won't be any indicator left. So this is the barium diphenylamine sulfonate is effectively reduced by the Fe2+, and so the Fe2+ itself is oxidized. So that's how we know what's going on. Okay, and then part C says this method of determining ethanol concentration does not give very reliable results, although the titration is very accurate. Suggest one reason why this might be the case. Explain how the measured concentration would differ from the actual concentration of ethanol. Right, this is pretty tough. So what we need to say is that actually this reaction, remember we said was an equilibrium reaction. We just left it for several hours. How do you know if the reaction is finished? It's really difficult to tell, and not all of the alcohol that you started with will have been oxidized, which obviously wouldn't give you accurate results. Even though the titration itself is the actual the setting up and leaving for several hours is obviously it's difficult to tell. I mean, the alcohol would obviously oxidize to an aldehyde. They're both colorless liquids, so it's really difficult to tell if the reaction has actually gone to completion. So that's the first thing we're going to put on there. You could put something like not all the alcohol is oxidized. It might not be. Some of it might be. Some of it might not be. So obviously that's not going to give you a true value. And obviously, if not all of it's oxidized, then we're going to have a bit of a problem. And effectively, you're going to have less potassium dichromate will be used up. Yeah, because obviously you don't have a large amount of your aldehyde, which effectively your alcohol will oxidize to. So yeah, so we need to put that on there as well, because obviously not all of it has been oxidized. So we'll put hence less. Remember, your potassium dichromate is your oxidizing agent. So this is the one that's going to be responsible for oxidizing the alcohol to your carbonyl group. Now, if not all of it has oxidized, then you're not going to use as much potassium dichromate, are you? So that's where we're coming from. All right, okay. And then obviously, what effect will that have on the actual titration? Well, obviously the impression you get from this when you do your titration is because less potassium dichromate has been used, it looks as though the ethanol concentration is low because you haven't used much dichromate. And that's what you're measuring in your titration when you do it. So it's like it had a knock-on effect. So this is why in science you have to make sure that every stage is really, really precise for that reason. Otherwise, it does have a knock-on effect later on. And you get results, and you think, well, that doesn't make sense. Why isn't that the same amount? And it's probably because of this step here, or something like that. So, yeah. Right. Okay, so what you get this impression that it appears low, when actually in reality, you do have, if you'd left it a bit longer, you might have had a chance for the dichromate to maybe oxidize a bit more of the alcohol, and so therefore you would get a more accurate view, a more accurate value of your ethanol value. So yeah, so get 3 marks here. So you get 1 mark for saying that it's really difficult to tell that it's complete because of the both colorless liquids. It's really tough. Therefore, we'll use less potassium dichromate, and the impression that would give is that your actual ethanol concentration is low compared to what it should be if we'd left the reaction a little bit longer to oxidize. So there we go. That's the end of section B. So on to the last section. Hooray, section C. That question was out of 16 marks. So on to section C and question 22. Okay, so this is section C, or question 22. And it's given us quite a bit of writing here, or a bit of information. And it's about metal complexes. So let's just quickly have a quick scan through this. So it says complexes involve ligands forming dative covalent bonds with a central cation, and the number of dative covalent bonds is the coordination number of the cation in the complex. Complexes may be positive, negative, or neutral. The ligands may be neutral or negatively charged, but are never positively charged. The ligands must have a lone pair of electrons. In some complexes, the central atom is neutral, as is the case with nickel carbonyl, which is used in the Mond process for the purification of nickel, and they've given us the equation there. So the formation of complexes is typical of transition metals, but other elements also form complexes. Zinc, which is a D block element, but not a transition metal, and aluminium, which is a group 3 element, both form complexes. Transition metal complexes are usually colored, but if the interaction between the ligand and the central ion is very strong, then the resulting complex may well be colorless. This is the case when with the complex FeF6-3-. The ligand in a complex affects its redox properties, and this is apparent from considering the relevant standard electrode potentials. For example, with copper-2 species, and you see we've got the 2 equations shown as the electrode potentials of the equations. So these complexes are industrially important, for example in the purification of nickel mentioned above, and in the extraction of gold, which involves the complex AuCN2-. Okay, so, and the last paragraph, it says complex formation is used in estimating the concentrations of metal ions in solution. Examples of this are the use of EDTA in titration and dimethylglyoxime in gravimetric analysis. Try to say that one quick. Complexes are also used in qualitative analysis, for example, intolerance reagents. This reagent is usually prepared by the addition of sodium hydroxide solution to an aqueous solution of silver nitrate, followed by aqueous ammonia. The resulting solution contains diamine silver 1 ions. Okay, so they've given us loads of information there, and obviously they're going to ask us questions on some of this information that they've given us. Right. Okay, so let's start with obviously part A. So it says the hydrated copper-2 ion is classed as a complex, but the hydrated sodium ion is not. By considering the interaction between the water molecules and the sodium ion, explain why the hydrated sodium ion is not considered to be a complex. Right, it's 2 marks. I mean, the first thing really is that we need to understand how these things work. So we've got a water ligand. The ligand has a lone pair of electrons. there's a delta negative on the oxygen, and in complexes we have a dative covalent bond that is formed between the oxygen and the metal ion in the middle. Now with sodium ion, you don't get a dative covalent bond, you actually get an electrostatic attraction because you have an ionic interaction there with sodium and another metal. So we don't have a covalent bond forming, so a dative covalent bond forming. So we have an electrostatic attraction, and so therefore we don't actually form a complex. So let's write that down. So let's say the oxygen atom on water have the delta negative charge. That's really important for mentioning that. So my pen's just about to run out. Let me just grab another pen. That's typical of that. Okay. Okay, right, just make sure this works. That one doesn't work, right. Alright, okay. What is I write in green? That's what you get when you get a cheap pen. Okay, there you go. So charge and where were we? Right, so oxygen atom on water, they have a delta negative charge, and we need to say that and forms and okay, so it forms an electrostatic attraction with a sodium ion. Alright, okay, so we get 2 marks for that. And 1 mark comes obviously from the oxygen forming a delta negative charge, and then 1 for talking about we have this electrostatic attraction. So we don't actually have a dative covalent interaction there. So you get 2 for that one. Okay, so let's say suggest how the aluminium ion is able to form a dative covalent. Suggest how the aluminium ion is able to form dative covalent bonds in its complexes, such as AlF6-3-. Now, what we need to say is that for something to accept these electrons, we need orbitals that are empty, and obviously these are going to be in the d orbital, or the 3d orbital in this case. So what we need to say is that there are the additional lone pairs from the ligands are accommodated in empty d orbitals. Oh, I picked up the wrong pen. Right, so we're going to put okay, so additional lone pairs are accommodated. 2 cots and 2 mattresses, that's how I remember accommodated. So in empty d orbitals. Alright, okay. So there you go. So that gets you that's just 1 mark. So it's pretty straightforward, to be honest. Okay, and then this one is a bit more stockier, this one. So transition metal complexes are usually coloured. Explain how the colours occur. Right. Well, the main thing here is you need to understand that the d orbitals, when we add ligands to them, the d orbitals actually split, and this splitting creates an energy gap by which electrons can migrate from a lower energy to a higher energy level, and when they jump back down, effectively a complementary colour is transmitted back out. So we've got loads of different points here, so they just want you to basically like highlight these points. So I'll start with by saying that the 3d orbitals, because that's what we're talking about here, are split, because that's when we've got ligands attached to them. It is talking about complexes as well, so that kind of gives it away a little bit. And we then need to say that the electrons, like I say, can move. So let's put that there. Electrons can move from low to high energy orbitals. Okay, and what they do is these electrons. So if we just draw a little diagram here, so we've got three. Let's say we've got 3 electrons down there and 2 up there, 2 orbitals. This electron, let's say that's sitting in here, can jump this gap here. I'll just put delta E there. So this is the energy gap between the lower energy levels and the higher energy levels. And providing it gets enough energy from a frequency of light energy, for example, it doesn't have to be light. It could be ultraviolet as well. But if it's got enough energy, then this electron will then jump up into this higher energy level gap here, and that obviously that frequency of light is then absorbed by the electron, and then what's emitted or what's transmitted, should I say, not emitted, is the complementary color of the color that's being absorbed. And you'll have a color wheel, and you can work out the complementary color. It's just the color that's opposite it on the color wheel. You don't need to worry about this for chemistry, thankfully. So yeah, so obviously the third point we need to say is that these absorb energy at a specific frequency, and then as a result, obviously the color, we're talking about why they are colored, so we need to then just say that the complementary color is transmitted. That's a really important word. You can say released, but transmitted is the proper word, really. There is 4 marks here. So we get 1 mark for saying that the 3D orbital is split. We get 1 mark for talking about the fact that the electrons can move from a lower energy level to a higher energy level state. You can say that they are being promoted to a high energy level state. Anything like that will do. Absorb energy at a specific frequency, so that's the frequency of light that effectively comes in, it comes into there, and that makes that electron have enough energy to jump to that higher energy level state. And then obviously we get this complementary color is transmitted, and that's obviously the color that we see. That makes the transition metals quite colorful. Okay, so next bit. Okay, so it says, why are zinc complexes such as Zn NH3 colorless? The simple reason is that let's get the periodic table. Let's try and grab one. There it is. Periodic table. There you go. So you can see the periodic table. The zinc is over here. It's got 10 electrons in its in the d orbital. It's full. Now, if it's full, what that means, if I just come back to this diagram again, like this one here, it effectively means that there's no space for any electrons to jump into these orbitals up here because they're full. So because nothing can jump there, then you don't have any color. So that's what we need to put there. So we need to put they have a full 3D subshell. So that's your subshell there. You can see it's full, so you can't have any electrons moving into it. Okay, right, on to the next part. Alright, okay, so this is part 3. So suggest why these strong interactions between the F- ligands and the Fe3+ ion result in the complex FeF63- being colorless. Right. Right, very strong interactions or between the F- ligands and the ion. The reason why this is pretty colorless is because that energy gap that I talked about before is so big, and because it's so large, the energy that's absorbed is actually outside the visible region, and we just can't see that energy. So yeah, so that's what we need to put. So put orbital energy gap is large, and then we need to say actually that the energy absorbed is outside visible region, so we can't see it. It's invisible. There you go. Right, 2 marks. 1 mark obviously for saying that the gap's too big. and then 1 mark for saying that actually it's outside our visible region, outside the visible region, so we can't see it, so it's invisible to us. Okay, right, and then on to D. Right, so he's used the standard electrode potentials given in the passage to predict whether it is feasible for thiosulfate ions S2O3 2- to reduce copper 2 ions to copper. Consider the case when the copper 2 ions are dissolved in water and when they are dissolved in aqueous ammonia, and give the chemical equations to support your answer. So we've got 3 marks here. Now we're going to come back to this anti-clockwise rule that I think is really, really useful. It just helps clarify things. Now with the anti-clockwise rule, you're going to use 2 equations, 2 half equations, and we're going to write the most the most negative E0 value on the top, and then the most, obviously, the next negative one, least negative one on the bottom, or the most positive on the bottom. So the first thing we're going to do is, obviously, we're talking about thiosulfate. So we're going to do thiosulfate, and we're going to do the copper with water here. So let's bring this sheet back here. So this is the equation here. It's useful if you have this in front of you, or if you're trying to remember this equation here. We're going to use this equation with thiosulfate, and we're going to use this one with the ammonia in thiosulfate as well. And we're going to basically say which one's feasible and show the equations for them. Now, take note of this number because we're going to use this one. So we're going to use the thiosulfate one, which was 0.09, and we're going to use this one, which is 0.34. So what we're going to do, I'm just going to leave that there so we can see it. So we've got our 2 equations. So let's write our thiosulfate one was the lowest E0 value out of the other one that we just seen there. So we're going to write that one up first. So we're going to put S4O62-, and we're going to, obviously that's going to react with 2 electrons, and that's going to form your 2S2O32-. Okay, and we said that one was plus 0.09 volts. Okay. The other one was your copper complex, and that was on the other sheet. So this is going to be your H2O6 2+, and that was plus 2 electrons, and that's going to form copper plus 6H2O. Okay, and that one is 0.34. Now, how the anti-clockwise rule works is pretty straightforward, actually. So if we look at our 2 equations, most negative always on the top. We'll just put volts on the end there just to clarify that. So most negative on top, and what we're going to do is going to go round like this. Start from the right-hand side, like anti-clockwise. So we're going from here, and then round here, and then through to there. And what we're going to do is write an equation. Basically, this is the only equation which is feasible. This is the feasible reaction. So the anti-clockwise rule tells you this. So what we're going to do is going to take the start of the arrow here and write this reaction down here. Make sure electrons balance, which they do. There's 2 and 2, so they just cancel out. So this is going to be 2S2O3 2-, the thiosulfate, and we're going to react that with the tip of the arrow here, or the start of the arrow for this side. So that's going to react with Cu H2O6 2+, and there isn't anything on here, and this is going to produce S4O6 2-, and we're also going to produce, see, that's the head of the arrow. Here's the head of the arrow here. That's also going to produce copper plus 6H2O, because there's the 2 heads. So you just write your products, whatever's at the head of the arrow, on there. Now, this reaction, you can see that the thiosulfate, which is this one here, S2O3 2-, is actually reducing the copper 2+ ion complex to copper. So this one is a feasible reaction. So we're going to, yeah, we'll write this in here. Okay. Okay, yeah, we'll put this here. So, feasible reaction. Okay, so we're going to just put a tick there to say this is feasible reaction. It also asked us to do the one with ammonia as well. Now, if I just bring that sheet back again, remember this one here. There's your thiosulfate, which is plus 0.09. Your one with ammonia is now minus 0.05. So this one needs to go on the top, and then the thiosulfate one goes underneath. So we're going to write them down there. I'm just going to nudge that up so we get a bit of space. Okay, so the first one was the copper one, sorry. So we're going to put Cu. No, that was H2O. 2 of them. NH3, 4 of them. 2 plus 2 electrons. These are big equations. These should be reversible, by the way. So this is going to be this is going to produce your copper plus 2 H2O plus 4 NH3. So effectively, these are just the ligands that were attached to your complex. And we said that one was 0.05, so most negative at the top. And then our thiosulfate reaction, obviously, is just that one there. So it's going to put S4O6 2 minus plus 2 electrons, and that's reversible. 2S2O3 2 minus, that's supposed to be 2. And this is plus 0.09 volts. Right, anti-clockwise rule. So we're going to start from the right hand side and let's swoop along to there and then swoop along to there. So our start of the arrow, let's write our reactants, which is going to be Cu plus, oh, make sure we cancel out our electrons. Cu plus 2H2O plus 4 NH3, because that's all at the start of the arrow here, and that will react with this as well, S4O6 2 minus. Okay, and that will form our product. All this is reversible. Our product is this massive complex, a copper complex, with H2O2, NH3 4, 2 plus, and we're going to produce this as well, 2S2O3 2 minus. I think I need to write smaller. Okay, so you can see that this is the feasible reaction going forward, this one here, and you can see that actually this one doesn't show. It doesn't show that the copper 2 ions would react. So it basically says it wouldn't show that the copper 2 ions are reduced to copper. This is showing that the copper ions are oxidized to copper 2 plus. So this one shows that actually in the ammonia reaction, that this one is not feasible, and this is because it is moving in the opposite direction. So we're just going to put that on there as well. So we'll just put not feasible. Okay, so there we go, and you get 3 marks for that. So you get 1 mark for writing down your 2 equations here. You get 1 mark for saying that it's actually feasible, and then you get 1 mark for saying that this one isn't feasible, but you are still showing your equations. It is important that you show your equations as well, because it does say right at the start here, if I just pull this down, it does say give chemical equations to support your answer, so that is an important part. Okay, I quite like the anti-clockwise rule because it really does show clearly. You get your equations down, it shows clearly how you work it out as well. There are other ways in which you can do it as well, but there you go. Right, and then on to the next bit. Okay, so this is question E. So it says the proportion of nickel in nickel, an alloy of nickel and silicon used in thermocouples, may be determined by the following gravimetric analysis. So it says finely ground nickel is dissolved in concentrated hydrochloric acid, and after neutralization, excess dimethylglyoxime dissolved in ethanol is added to the solution formed. The resulting red precipitate is filtered, washed, dried, and weighed, and the equation for the formation of the precipitate is shown obviously below. So we've got this massive equation. There's our big complex there. Okay, so it says state the coordination number of the nickel. Coordination number is the number of coordinate bonds, not the number of ligands. So the number of coordinate bonds here is 1, 2, 3, 4. Got big arrows on there, so it's a big clue. So the answer is 4. Okay, and the next section. So it says in an experiment, 1.02 grams of nickel formed 4.82 grams of the complex. Calculate the percentage by mass of nickel in the alloy. The molar mass of the complex is 288.7 grams per mole. Right. Okay, so the first thing we need to do is work out the number of moles of complex first. So let's work that out. So let's put amount of complex. Okay, because what we're going to do is work out the amount of the complex, and then we're going to work out the amount of mass of nickel in that complex. Once we've done that, then once we work out the mass of nickel, we'll then just do a simple percentage calculation. So that's the thinking behind it. So to do that, we need to work out the actual amount of the complex first. Now we have a mass. So number of moles is mass over mR. So the mass is 4.82 grams for the complex. Just put grams on the end there. The mR is 288.7. And then we're going to obviously put that on a calculator. Let's put a calculator in here. So it's 4.82 divided by 288.7. There you go, bang. So that's 0.16695. Let's just leave it as that. Okay, so that's the number of moles. Okay, so that's the number of moles we have of the whole complex. We need to work out the mass of nickel though, because that's effectively what we need to work out. So mass of nickel is going to be the MR of nickel. So the MR of nickel, or the AR, sorry, not the MR, so it's an element. So the AR of nickel is 58.7, as you can see on there, there's nickel. Okay, so it's going to pull out of the way. So that's going to be 58.7 multiplied by the number of moles in the complex. Remember, that's also the number of moles of nickel, because obviously you have one nickel for every complex. So that's going to be 58.7 times by 0.01666955. Okay. Calculate it back in again. 58.7, multiply that by 0.016695. There you go, 0.98003. Let's just stop there for that bit. Okay, so that's going to be 0.98003, or you could just put 0.98, to be honest, that should be enough. And that's in grams. And then all we have to do is you then just need to work out the percentage of nickel in the alloy. This is just very straightforward percentages. So this is the amount of nickel, 0.98, just leave it as that. And we're going to divide that by, now it said that we had 1.02 grams of nickel, of which 0.98 are nickel. So obviously the rest is made up of other, so obviously silicon. So 1.02 times that by 100. Bang, there you go. Let's put the equal sign in, bring the calculator back in again. So lots of calculations in this. So we're going to put in 0.98, divide that by 1.02 equals, times that by 100. Go, and so we get a number 96, as you can see, 96.08. And that's obviously in percent. Okay, so marks, 2 marks for this. 1 mark actually for working out the mass of nickel. And to do that, you need to work out the moles. So actually you get 1 mark for that. And then you get 1 mark for obviously your answer, your percentage. So you get 2 marks in total for that bit. Okay, right, that's the next part. Oh, it's the last page. Okay, right, so part F. So it says, suggest why the nickel carbonyl complex is used to purify nickel ores. Well, if we come back to this, just this bit back here, if we look at this, the reason why it's used is actually the this here is a gas, and so therefore it's really easy to separate from the nickel. So that's the reason why we do it. So I'm just going to put that on there. There you go. So it's easily separated. So you get 1 mark for that. And then on to the last bit. Hey, last question. Okay, so it's G. Use the equilibrium below to explain why ammonia is used to prepare Tollens reagents as described in the passage. Okay, this is quite tricky. That is really difficult. So, okay, so obviously Tollens reagent is this. Here's our Tollens reagent. We've got the silver with the 2 ammonia ligands attached to it. Now, what we have to say is, why are we using ammonia to make this? And I suppose the key thing here is like a hidden message is equilibria. We have to use the equilibria. So we have to talk about Le Chatelier's principle within these questions, or use Le Chatelier's principle to help us understand what's going on. Okay, so the whole point of this is actually using ammonia prevents the formation of this stuff here. Okay, so if we use the ammonia, it basically allows any Ag plus to react with the NH3 to form AgNH3 So and it helps to slow the amount of this down. So that's the first point we need to make. Okay, so ammonia prevents the formation of this stuff, which is Ag2O. Okay, so that's the first thing. Also, if we think about it, if we add ammonia, what this does is it actually shifts the equilibrium to the right, because the equilibrium will move to this side. This is the product we want, remember, this one here. We don't want any of this, we want this. So it'll shift to the right. So adding lots of ammonia will do that. But also, what it will do is it will actually decrease the amount of Ag+. And obviously, when we decrease the amount of Ag+, this will form this equilibrium to the left. So therefore, we get less of this. So by decreasing the Ag+, the reaction will shift to the left in this top reaction here to replace the Ag+ that's been used up because we've increased the amount of ammonia. So it's all kind of like having a knock-on effect. So let's get that down. So addition of ammonia shifts equilibrium to the right, or you could say we have a decrease in the concentration of Ag+. Okay, so we could say that, and because we have a decrease in that, then what we can say is the equilibrium in 1 equation 1, which is this one here, shifts to the left to replace the Ag+ ions. You see this one here. So if we remove these two equations are quite linked together. So in fact they're in the same beaker. So that's how we know they're linked together. So if we increase the amount of this will react with this and obviously pull the equilibrium to the right, because equilibrium will try and remove this. And as a result, the amount of Ag+ drops. In this equation, if the Ag+ drops, then equilibrium will shift to the left to replace it back again. And so therefore, hence obviously we're not producing much of this. So we're working it both ways as well, and that's obviously what the ammonia does. It does quite a bit actually in this reaction. So marks, right? It's 3 marks. We get obviously I've tried to split it up so you can see where the marks obviously fall. So you get 1 mark for each of one of them points on there. So that's a pretty tough question because there's a big reliance on you knowing obviously how equilibrium works. But there we go. That's the end of the paper. It's a 90-mark paper. I hope you did reasonably well in it. And make sure to read the questions really carefully, as you can see. And calculations are obviously very, very important in this. That's it now. Bye bye.